So I thought I would bring this up closer. This has 8 design features of HDI that you don't use in multilayers. So I thought I'd collect together. So if nothing else from this course, if you could go back and use 1 or 2 of these ideas. If you can use 4 or 5, you're going to be even better. If you can use 6 or 7, that's fantastic. I don't expect people to use all 8 unless you've got a really lenient boss that lets you take risks. All 8 work, but you'll see as we go through, they get kind of more and more radical until ones that, I don't know if any of you have read the papers I've written on the elimination of ground planes. Anybody read my paper? Okay. Well, guess what? You don't need, the elimination of power planes. You do not need power planes anymore. How many here believe that? Nobody raised their hand. Okay. Well, I can prove to you, you do not need power planes. There's a better way to do it. How many here are risk takers, I should say? Anyway, okay. How many here have a liberal enough boss to allow you to experiment or take risks? Okay, good. Then all you that raised your hands, when we get to the point where I show that you do not need power planes, and there's a better way, print out those slides, put your name on them and things like that. And if you have an applicable design, and go to your boss to say, boss, I've got a good idea. If he wants to know who else uses it, you can reference my technical paper and tell them that Hewlett-Packard does it. And Hewlett-Packard's been doing this since 1997. But in Hewlett-Packard, it's a company secret. We didn't patent it. If we patented it, everybody would know about it. Instead, it's a company secret. And my non-disclosure means I can't talk about company secrets for at least 10 years from my retirement date. Well, I've been retired more than 10 years, so I can tell you about it and not violate my NDA. Like IBM, in Hewlett-Packard, we didn't patent all of our greatest ideas because you have to disclose so much information in the patent that everybody understands it and you can do a workaround. So what you do is you just keep it a secret. And you would wonder that sooner or later somebody would take apart Hewlett-Packard computers or instruments and figure out how are they doing this. And they would realize, we don't have any power planes. You know, well, how can HP do this? How can they be at 80 gigahertz and not have a power plane? Well, because it's RF circuitry and we use coplanar power delivery. Anybody here with an RF background understand coplanar waveguide power distribution? Well, if you're an RF guy, you say, oh, that's not new. We've been doing that in RF radio since World War II. Yes, I agree, you have. But in the digital field, we've never done it. We've always used planes. And you don't need power planes. So I'll go into, and so if you can understand, if you don't need power planes, how many other things are you doing that you don't need to do because we've always done it that way? So one thing I like about our industry is that we're still using technology that's 60 years old, like lands on the vias. How many of you here believe that you have to have a land on a via? You know, well, you all should raise your hand. You don't need a land on a via. We use lands because we used to have components we put through the holes and we crimped them and we would solder to the land as we crimped the actual lead. Well, when we went to bulk array and surface mount, we're not using holes anymore. You don't need a land. In fact, I've got lots of research data to show as you shrink the size of the land, the hole becomes less and less reliable. And that many of you are skirting on the edge of producing designs that will not last a year or 2 in the field because you're using too small an annular ring. The annular rings have to be big or they have to be 0. So that's also in here. How many of you are brave enough to try landless vias, which is We learned that from our Japanese partners in about 1986 and implemented it about 1992. Hewlett-Packard started using lambless vias. So if somebody had bothered to take apart our stuff, they realized there are no LANs on any of those vias on an HP multilayer. That's one reason why it costs half as much and works twice better than what they can design. The LAN is an artifact that we should have got rid of a long time ago. But I'm not going to convince you. You can do it the old way. But beware of the people that experiment with the new way, because they'll put you out of business with newer techniques. So we're going to kind of talk about these 8, number one, where to place the blind via, BGA breakout, reduction of the big drilled vias for power and ground, automation of routing or incremental, horizontal, vertical micro via routing pairs. If you can get 2 layers of micro vias, horizontal and vertical, there's a big advantage to that. Just simply finer traces, spaces, vias, and pads for miniaturization. Buried capacitance and decoupling cap removal. And last, the split power plane supply with blind vias. And essentially, I'll show you that there's the RF method of distributing power is much more efficient for high frequency, especially 5G electronics, than using a plane. You've got to get rid of these damn planes if you're going to stay in this business. And that's because of frequency. And the RF guys will explain to you why that is, that when you're dealing with 60 or 80 gigabits per second for 5G, that is RF frequencies. You're radar designers now, not computer designers, you're radar designers, and you've got to start applying all of the RF rules that only a small group of electrical engineers deal with in terms of RF. Now everybody has to deal with it because of the rise times involved. And my advantage was that I recruited a number of RF engineers into our design organization. And they really helped revolutionize how we looked at printed circuit design, but also designing integrated circuits helped revolutionize how we design the printed circuit. Taking from those other industries and bringing some of that wisdom into what we were doing. One of the first questions I ask is, what density are you getting? Does anybody here actually measure the density of their finished printed circuit design? Most people tell me they don't. So working with different companies, typically a through-hole board will get 2.6 to 6.8 inches length per square inch. I apologize, I haven't bothered to convert these to centimeters per square centimeter. And you're not going to convince the Americans off the imperial system to the metric system, even though they should be using metric. We're still kicking and screaming, inch by inch into the metric arena. And in fact, we've contaminated the people working with the Taiwanese. When I talk about centimeters and microns and things like that, the Taiwanese ask me, how many mils is that in inches? And I said, what? You guys should be using the metric system. What do you mean They said, well, all of our customers are American, so everything has to be in inches and feet. I said, well, give the Americans the meters and millimeters. Force them to change. Somebody's got to change this. And so customers, if they take this class, I ask them to tell me if they've used any of the principles. And they're starting to report that they're getting 15 to 21 inches per square inch routing on the HDI layers. I will tell you that from this class, I guarantee you can get 2 to 3 times more routing density. They're actually telling me they're getting 3 to 4 times. I won't guarantee 4. But 3 or 4 or 5 times is possible, because a lot of you are much smarter than I am. When you start to use it, you'll figure out kind of a better way than we haven't necessarily figured out the best way. And it's interesting because on the far side of a HDI board, they're reporting 10 to 14 inches. And so there's definitely a side one preference on placement of parts. So one side of an HDI board is a higher density than the far side is. And that simply is either because of assembly test, whatever it is. They're not perfectly balanced, and maybe will never be perfectly balanced. One side, there's always a higher density than the other side is. And that they go from the 6 to 8% routing efficiency to 20 to 28% routing efficiency. So they're starting to use the metrics that I've introduced to talk about a design. They don't talk about lines and spaces and hole size. They talk about layout efficiency and total number of traces per linear centimeter, or something like that, because those are a better measure of performance of the design. And if you want, how do you get that number? Well, like I say, to get the total trace length per layer, select all the routes on a given layer. Usually the lower left-hand status window gives the total route length divided by the routable area. And the routable area is usually available from the design report kind of thing. So in the HDI guidebook for Altium and the HDI handbook are the equations and what the actual equations are and how to collect these various things. So a lot of the people asking the questions because they have money are the military and space. So I get more questions from the military and space than I do from the mobile phone or the telecom guys. And so you remember that chart I showed you with the line? Look where the military and space guys are. They're on that other side. An example is this one right here. This is one of your products. This is the NATO radio. So this is the NATO helmet radio where we put the satellite radio in the helmet of the soldier. And the original design was a 16-layer with mechanically drilled blind and buried vias. And on the top there, and we went to a 12-layer HDI board on the bottom, mainly because the devices were 0.5 millimeter pitch. And I don't know if it shows up very well where that is. See, that's way up there, way on the other side of the HDI line. They tried to do this with mechanically drilling blind vias, which, talk about costing a fortune. So there are some of the, there's 996 parts, 5,332 pins, it's 102 parts per square inch, 5.34 average pin per part, and 545 pins per square inch. So that's the log scale where it's sitting. They never collected that numbers, and because that's the first question I asked, always the first question. Well, how big is the board? How many parts have you got? How many pins, and what's the pitch? And invariably, when they throw out those numbers and said, now tell me again why you're doing this construction. And they said, well, because that's only what our fabricator can build. Well, I said, that's not a very good reason. There's lots of fabricators. Does your fabricator have a laser? No. Well, have you qualified fabricators that use lasers? Yes. Well, what do they say? Well, we never asked them. Well, okay. So number one, where to place the microvias. In multi-layer, conventionally, we always look at the peripheral. In HDI, if the device has less than 400 pins, then the best breakout will be peripheral. If it has more than 400 pins, you've got to use a new technique that doesn't work in multi-layer, but does work with HDI. And that's these diagonal L-shaped or V-shaped. And so rather than using the perimeter, we create channels and routes into the board. if there's 400 pins or less, then you can use the peripheral. But the peripheral over 400 pins just keeps adding layer and layer and layer. You must change the whole concept of breakout. And why we're going to do that is that, our via hole is very, very small now, typically 1.25 millimeter, 1.5 millimeter diameter laser drilled holes. They're not these 15 millimeter mechanically drilled holes. They're much, much tighter, and so they can be swung around. So here are various sizes of holes and various pitches. And is there enough room to swing them around even if they're mechanically drilled? And sometimes on the larger pitches like 0.8 and 1 millimeter, you can actually swing them and mechanically drill them. They don't have to be done with a laser. But as you go smaller pitch, that has to get closer and closer until you're at 0.4 millimeter, 0.35 millimeter. The via will always be in the land somewhere. There's no room for it to be outside the land. The pitch is just so tiny that we're doing that. Now, and some of the times, depending where you have enough room to do a ground flood. If you can do a ground flood, then you're going to save a lot of EMI problems. Putting ground on the surface and turning the PC board into a Faraday cage is a great way to eliminate the EMI. So if it's possible that if you have enough room to do a ground flood in order to make a Faraday cage out of the board, you've gotten away from, and I'll show you slides later about EMI problems and how HDI helps solve a lot of EMI problems. Because big through holes are big antennas that radiate enormously and create all kinds of havoc in terms of EMI noise. With that. And so swinging these vias, depending on the pitch and your SMT land size, and I can't define it because all of you may have different SMT land sizes and use different sizes of pitch devices. There's no way to predict what thing up. So I chose 0.65, 0.8, and 1 millimeter. Above 1 millimeter, there's kind of no need to have blind vias. 0.8 to 1 millimeter is the transition area. At 0.65, you have to use the blind via. So 0.8 to 1 millimeter is, you could go conventional through hole or it could go HDI. It's kind of your choice. Depending on your skill and other ones like that, there's no right or wrong way. But if it's over 1 millimeter, it's better to go conventional multilayer. If it's under 0.8, it's better to start using the micro via and swinging them. So one of the issues is on a blind via, which this is a better illustration, is that in order to get more routing on the inner layer, you notice that here, the end of the microvia hole is centered on the pad. But when I project that microvia up to the surface, where we have the SMT device pitch, the hole is not in the center of the land, and that's great. We actually don't want that microvia VN pad to be centered in that one. But because it's off-centered, we can get one trace on the surface, but underneath that, we can get two traces for routing. And the reason why you never want to put that VN pad in the very center is that if you choose not to use a hole filling option, and if the blind via is a hole fill, then sometimes that carries a 5 to 15% price adder. In other words, remember those original micro vias I showed you? They were conformal plating, but there is a opening in the center of even the tiny via. You could specify a hole fill in which solid copper will totally fill up that to the surface. But depending on vendor, you may have to pay extra for that. You don't have to fill the hole in, you know. So if you chose that you don't want to pay extra, you don't want to create a void. So when you're assembling this board and you're screening solder paste on the land, that solder paste bridges that microvia. When you put the BGA on top of it, during reflow, as that solder paste melts, the ball on the device drops to be like a cork in a wine bottle. And so there's no way for the air to escape the microvia, and that shows up as a void. Now, that's not a defect, but it does show up in X-ray. So it's not a blowhole, and it will not cause, and these are not blowholes from the old through-hole days of wave solder, but it does show up, and OEMs don't like to see that in their X-ray. Before we had really, really good X-ray, they didn't know it was there. And it's perfectly reliable, but with the newer generation of X-ray, three-dimensional X-ray, it shows up that we've got a void. So we still have a big debate in the IPC about, well, how much of a void is permissible? And all the microvias, that void size is permissible and approved for class 2 and class 3. But assemblers don't like it. But if you place the microvia off-center, then there's a route for the air to escape and the solder to flow in. And so there is no void there because the solder has flowed into the hole. But if the hole is in the very center of it and you've centered the BGA on it, you've kind of corked the bottle and there's no way for it to get out. So there's, I blame mainly it's not the OEM, it's the EMSs. You have contract assemblers. And I'm not a big fan of contract assemblers because contract assemblers, the problems are always caused by the designer or the fabricator. They take no responsibility for any problems that they caused or their lack of education. And so they like to push all the costs back onto the fabricator or onto the designer when it's really their fault. And so I'm not a big fan of dumb EMSs because most EMSs are really, really dumb. I'm from the days in which Hewlett-Packard and IBM and Texas Instruments assembled our own boards. And so we couldn't blame anybody but ourselves. EMSs being a separate company, that's never their fault. They always claim it's the designer's fault or it's the fabricator's fault. And in fact, it's their fault. And they're too cheap to learn how to do it right. And one of the things they haven't learned how to do is how to assemble HDI boards. They're still figuring out how to assemble multi-layer boards. They haven't figured out how to assemble HDI boards. So their rules typically add 15% to the cost of an HDI board because they're just simply dumb. They don't know how to do it right. And I know because I was the chief technical officer for the biggest contract assembler in the world, Foxconn. You know, we're bigger than the next 12 EMSs put together, 160 billion US dollars. So that's about 140 billion euros. 140 billion euros just in assembly, you know, for making the iPhones and the computers and the games and whatever it is. And it's in because in Foxconn, any blunder in assembly is picked up by Foxconn. We can't push the cost back to the OEM. And because essentially Foxconn is captive in that sense. It's not the same as a merchant. And so I made sure that our assembly process didn't artificially jack up the price of the BRPC board or invalidate the designs that you might have done. It's simply, you know, much smarter assemblers than I typically run into in terms of assembly. I'm harsh on assemblers, but they're frankly too lazy to learn to do it right. You know, they're too busy trying to make money to learn how to do it the right way. they don't mind doing it over and over and over and over the wrong way instead of learning to do it the right way. So the second of these is what I call boulevard routing for bigger BGAs. And that is that a big BGA actually has 4 different zones of breakout that you have to worry about. The outer perimetry, a transition zone, the very center power and grounds, and one like that. So we actually have A, B, C, and D zones. And each of these zones has a different breakout methodology. It's on a multilayer, it's north, east, south, and west. But on the big complex one with HDI, there's actually multiple different kinds of breakout methodologies. And a lot of it has to do with when you've got lots and lots of pins like this and mixture of power, ground, and signal, you've got to sit up here and calculate what is the distance and the angle of that swing. Like this one, this is a 1500 pin FPGA at 0.8 millimeter pitch. Well, it comes down to a simple trigonometric spreadsheet. You need to write a trigonometric spreadsheet, and if you can't do it, then go to your local high school and have the students write it for you, because believe me, you know, there's really, really smart kids at the local university or the local high school that can write these spreadsheets for you, even if you can't. So don't, you know, if you can't do this, but this is 8th or 9th grade algebra and geometry. This is not high mathematics. It's simply trigonometry. In order to figure out what should the angle be because of this size of land pattern and this size of via hole and this pitch, what should the angle be to get maximum clearance for my space? And you do it as a spreadsheet. Now, if you want to be particularly mean, force Altium to give you this, you know, kind of thing. I mean, I would take the simple way out and demand that Altium have this as something you can download and let Altium set it up and everything so you don't have to. But if they won't do it, any high school student or young college students majoring in engineering and math can make this for you. You know, so that the resulting BGA fan out, you've got the different strategies for the corner, the peripheral, the transition area, the center power and ground areas, and you end up with this Vertex 5, 1764 pins. Why do you do this? Because this takes only 2 signal layers to break out. And if you don't do it this way, you're going to have 6 signal layers and all the reference planes. So your multilayer is going to have virtually 10 to 12 more layers than it needs to have. And that's why I say you can do it the old way, still works, it just costs a lot of money, or you can do it the new way that has 12 signal layers less for the same, you know, the same PC board. Your choice. But there is better ways to do it. What does the 2 ones look like? Well, on this Vertex 5, you can see that, you know, we have a blind via from 1 to 2, we have a skip via from 1 to 3, and then we have a buried via from 2 to 11. Okay, so on layer 3 is the Rocket I/O, and so these are the Rocket I/O, which are all the single-ended devices. They are on layer 3. All of the differential pairs are in layer 5. And these are all the differential pairs. So Vertex manual says for you to do this in 6 layers. You know, I typically end up doing it on 2 layers and saving the money and everything with it. Because the problem with 6 layers, we now have crosstalk. We have a lot more crosstalk issues than doing it this way. One of the things is that you notice between the layer 3 and layer 5, this area right here, we've thrown in ground planes to isolate the micro vias from the through holes. And that's because the through holes transmit noise. So in the most sensitive nets, we try to keep them as far away from any through hole as possible because we pick up noise through the through holes. And we're already working with a reduced noise budget on these more modern chips. They're down to 3.3 volts and sometimes only 1.3 volt is the total voltage. And our noise budget has shrank enormously. So we've got signal integrity and noise issues all over the place. So we want to isolate our most critical nets. So as I'll get into, our most critical nets are always in the HDI zone, and our less critical nets are in the center of the board where there's lots of through holes kind of thing. So I'm a big advocate of annotating the schematic into sensitivity of the nets in terms of what electrical class are each set of what's going into this schematic. And so how can you do this? Well, the green pad there is the surface mount pitch. And you notice by going from 1 to 3 or 1 to 2 and then a buried via, we can route 6 more signal layers. We can get 13 traces between the blind and buried vias. On a multilayer, you only get 2 traces. Here, we're getting 13 traces. And you can do the 6 times more routing in the same real estate. So you can keep doing it the old way with 2 traces. I don't mind. But there is a mechanization where you can get 6 times more, which means you need less signal layers, which means you need less reference layers for those signal layers. And the multilayer collapses down to something that's easy to solder but more reliable. It's not as thick. So this is kind of how it looks like from the side. Some people have a hard time visualizing this. But you notice that down here, this is what I call the boulevard. This is the freeway of routing. When you get past all of the blind vias, the BGAs disappear. And it's like you have a superhighway across your board that you can route these things. So by proper planning of where you put your blind vias and your buried vias, you can create superhighway of boulevards. So I call that channels and boulevards for lack of another name. That allows much easier and faster. The biggest thing is you've got a lot more room now to do it, and you can finish your design up much quicker. And you can take advantage of the space if you want to reduce crosstalk, or if you have sensitivity on differential pairs and things like that. There's some of the things shows that, why do you have so many? Well, those mechanically drilled holes are now 4 times the pitch of the device you're working with. So if you use on a multi-layer, the holes are at the same distance as the pitch of the SMT. But here, the holes are at 4 times larger pitch than what you're working with. And that's simply more space to, so there it kind of shows you a close-up of where these holes are from 1 to 3 and from 1 to 2 and then 2 to 11. That's kind of what the fancy view in the 3D now viewers of what these things look like. So they're not looking like the conventional multilayer anymore because they're not the conventional multilayer. This is a whole new design strategy that's evolved and more complex than multilayers are. They're the next step. The step after this is when you start getting into semiconductor design. And I'll tell you right now, we do not have power and ground planes in semiconductors. Well, wait a minute. How come they work so well? They don't have any power and ground planes? Yep. You don't need power and ground planes, guys. Not if you understand fields. Because the semiconductors don't have any of them in it. And so as we started to experiment with semiconductor design techniques in the printed circuit arena, we found they worked better than the printed circuit design methodologies. So we kept stealing more and more design methodologies from the IC guys, and we started stealing their tools because they had better DFM tools than we did, and they had better planning tools than we had. The semiconductor guys kind of have all the great tools. Oh, I got 2 minutes. Great. Okay. So this is a top view of the conventional multilayer. You know, you're only going to get 2 traces between the vias. And so that, you know, from a side view, it looks like that. So that's not, you know, there are no 13 traces because the holes are in the way all the time. So the holes are not only in the way, but the holes are transmitting noise. Because I'll show you some graphs. Once there's a signal that has a lot of noise on it next to a through hole, it capacitive couples over, goes down the through hole, and then contaminates every single signal next to it on other layers. So through holes are really, really bad. They, you know, you need to get rid of them. If you get rid of 100% of them, that'd be great, because they take up a lot of space. They're the first things to crack for reliability, and they propagate noise all over. And any noise on the power supply, the through holes are going to pick it up and couple it to your traces. And so, you know, I'm against through holes now that I've got HDI techniques. So like I say, this is a through hole at 0.8 millimeter. There's no ground flood. It takes 4 rows, takes 5 layers. You know, the same device with microvias at 0.8, there's a good ground flood on the surface for EMI protection. The 4 rows take only 2 layers. There's no power plane voltage or impedance drop, you know, because we haven't turned the power plane or the ground plane into Swiss cheese. And so I teach a hands-on class with Altium in which you all get a workstation, and we're going to spend 2 days learning how to design HDI properly. And we're going to work with 0.5 millimeter and 0.65 and 0.8. And this is a board we typically design. I have it with me, but the problem is that if you don't have a magnifying glass, it's hard to see at 0.5 millimeter the swing breakout, because, I mean, without a magnifying glass, that's really small. But this is what everybody takes home after the 2 days on a memory stick, is their design of these HDI devices using the principles that we're going to talk about today. And here's a great free book written by a real genius in the field, Charles File, called BGA Breakout and Routing. You can buy it from Amazon, but it's also available free. So I recommend the free version, but if you want to pay for it, Charles will thank you. But there's a free version available. You can get it from iConnect 007 US, or you can get it from Mentor Graphics. When Charles wrote this, you can see at the bottom, he worked for Mentor. Charles, though, is the technical director of Altium. So we all kind of retired from Mentor at the same time and all went to work for Altium, including our boss, Henry Potts, retired from Mentor and is now the executive vice president of Altium. So, but I recommend this. It's free of charge. It's a must-read for if you're dealing with bigger, complex BGAs and the use of HDI, including the use of Japanese technology, which we'll talk about this afternoon. And with that, we're at coffee break.